Okay, today is the last and optional lecture of this class. It's about model selection, which is very important, not just specific to the generalized linear models, but also in general for parametric models in statistics. So what the model would you choose to fit your data? You could choose a rather complicated model with many parameters or a very simple model with few parameters. So this model selection is of fundamental interest to our statistical data analysis. So today we're going to introduce two very important criteria. One is so we're going to introduce two model selection criteria. One is what we call the AIC, and the second is what we call the BIC. So they share the IC, which means information criterion. And I think this name was first used in AIC. And AIC is standing for Akaike information criterion. And Akaike is the author's last name. I think he's from Japan. And this AIC invented this concept of using a criterion that is fit to the whole data set, that is applied to the whole data set, that which is used to fit the model. So in other words, in AIC and BIC, and B stands for Bayesian, so it's a later concept. And these two things share the property that they do not need data splitting. Versus something we commonly use in practice, the cross-validation, which requires data splitting. So you can see that the cross-validation is a very intuitive approach, which means that you don't use the same data for model parameter estimation and also model evaluation. So you use part of your data for model parameter estimation, which is also called model fitting. And you use a separate part, the left out part, for model evaluation. So the reason for doing that is we can avoid model overfitting. Because if we use the same data for twice, it is no doubt that the more complex model that has more parameters can fit the data, the training data, or sort of like the training data. But here I want to clarify that we are not specific to the supervised learning case. So that's why we don't say it's training data, but it's the data used to fit the model parameters. So if you have many parameters, you can always fit that part of data well, but it doesn't mean that the model is the most reasonable one. Because if you apply the model to some new data, then you see they don't agree well, which means that in the previous fitting stage, your model is fitting the noise as opposed to the true signal. So cross-validation is very useful because it's a very flexible procedure and it's generally applicable. However, its major drawback is data splitting. You know, in classic statistics, especially when we don't have, like in the social science research or biomedical research, we don't have many data points, or we can say the sample size is very small. So if we just do cross-validation, we will further reduce our sample size for model fitting. And that's something we want to avoid. So that's why in the previous classic stage and also in the stage without powerful computers, people invented AIC and BIC just as a very easy to calculate criteria. So as we will see that both AIC and BIC essentially only relies on the log likelihood of the MLE. So once you have the MLE of your parameters, you plug them back into the log likelihood. With that, you can calculate AIC and BIC immediately. So there's just one fitting after all. While using cross-validation, let's say 10-fold cross-validation, you will do 10 fittings, and then you will do 10 evaluations. So I would say the major advantage of AIC and BIC is that it doesn't require data splitting, so it saves your sample size. But you must know that there's always no free lunch. So the price you pay for not splitting the data is to add some requirement or assumptions. So AIC and BIC are not assumption free. And especially, I wouldn't say AIC is not assumption-free, but AIC and BIC are both approximations. So you are doing a lot of approximations in the establishment of these two criteria, and we'll see that very soon. Okay, so before we talk about their technical details, I want to give you some shorthand, I would say, preview of their advantages, theoretical advantages. Okay, so the relative or theoretical advantages of AIC and BIC is that for AIC, it aims to find the model that gives the best prediction accuracy. So we're going to define what do we mean by prediction accuracy here. So as we'll see very soon, this means the minimum KL divergence, okay, between the chosen model data density. So basically, we're going to evaluate the density of our data, or probability density of our data, given the chosen model and the true density, true data density. So we'll see that very soon. So in other words, there is some true probability density for us to generate the data, but we don't know that. And we can also have the density calculated with the model of our choice. And we want to say that these two densities, KL divergence, should be as small as possible. And AIC can always find the model that gives the best prediction accuracy defined in this way. Okay, so at least this is the theoretical guarantee we want to achieve with AIC as our sample size goes large. That's AIC. And BIC is taking a more, I would say, aggressive goal. So its goal is to find the true model among the candidate models. So you can see that in the concept BIC, we are under the Bayesian framework, which is the B. So what it means is that we want to evaluate the posterior of each model given the data. And we want to pick the model that has the largest posterior probability. So this approach has a nice theoretical guarantee, that is, if there is one model among your candidate models that is the true model from which your data are generated, then BIC can, using the BIC as your sample size goes to infinity, you can find the true model. So that's the theoretical advantage of BIC. But after we introduce those two, we will revisit this concept and we will talk about some controversy about which one is better. Okay, so we'll revisit that later, but this is just a preview. So what's next is that I'm going to introduce the technical definition of AIC, which is not easy to find in many introductory textbooks because they just introduced the formula of AIC without the detailed explanation of why we have that formula. So that's what I'm going to do next. So in the original AIC paper, as we said, it's an information criterion. And this information criterion is because of the use of KL divergence. This is a concept that is from the information theory. Okay, so let's just give you the following notations. So let's say that we have our data. We're going to stick with this throughout this lecture. So let's say that our data is Y1 to Yn. They are IID from a true density, okay? But we don't know what it is. F is unknown. What we propose is K candidate models. So let's just write them as M1 to MK. And they have, each of them has a set of its own set of parameters. Okay, and so their number with number of parameters, we call that D1 to dk. Okay, so therefore, specifically under model J, the PDF of each yi is, we write it as this P, and the argument, we just put yi in that, and which is under the parameter, I'm just going to use this notation, theta j. Okay, so with number of parameter d1 to dk, so which essentially means that we call the parameter theta j and its dimension is dj. This is what we mean. So model J has parameter theta j. So if we want to define the KL divergence, okay, so what we want to do is to contrast F with this P. So essentially, the KL divergence of MJ, in contrast to the true model, the true density F, we write it as the expectation under Y following this, for Y following the true density F. So here we just consider one observation, one data point, okay? And that KL divergence is just the log of Fy divided by the density of model J. Okay, so by this definition, if we further separate the log ratio term, we're going to have the expectation of log Fy minus expectation of log Py theta j. Okay, so essentially, you see, if we want to minimize these two things, and just note that this expectation is also under F. So clearly, the first term has nothing to do with our model selection, but the second term does, right? Because J is involved in the second term. So then what we really want to do to minimize the KL divergence is becomes equivalent to maximizing the second term without the negative sign. So what we want is to choose J, okay, by maximizing over all the possible J, we want to find the one that maximizes the expectation. Okay, and here I'm just writing down one observation for convenience, but please note that essentially we need to have y1 to yn here and y1 to yn here. So it's just that I didn't write it out because otherwise I will say I will use the IID so that I get product here, I get a product here. So then I will also have a product here and it becomes summation after the log. So to be exact, what I really want to say is if you take that thing, so if you have the y1 to in the product and summation, so it's, maybe I should write it out so for better clarity, or I should say max j, okay, and then we're going to have summation I from 1 to n, expectation log Fyi given theta j. That's it. If we have n data points, that's the formula we're going to use. And here's just one for one observation. Okay, but the problem here is that, you see, there are two things we cannot evaluate. We don't know F. We don't know F. So that we cannot really calculate this expectation exactly. And we don't know what's theta j. the parameter of model J. These two things are both unknown, and we need to use our data to estimate them or approximate them. Okay. So this requires to use data for twice. So how do we estimate theta J from our data? Clearly, the most popular approach, and that's the approach we introduced in our class, is to use the MLE. So if we use the MLE to estimate theta J, what is that? Estimate theta J by MLE. So we can actually denote that as theta J hat. And that is trying to maximize this. It's actually the, oops, I think I made a typo, sorry. This is P. This is P, yeah, it's not F, my bad. So it's going to maximize, so it's the theta J that maximizes the summation of log of P yi theta J. This is exactly what we define as the log likelihood. Okay, that's how we obtain the MLE. And then how about the expectation of F? So the most natural thing to use is to use the sample mean as an estimator for the expectation, right? So that's what we do. So we estimate this expectation of F by the average over all the points, right? So let's say this. We're going to do that. So essentially, what we are going to have is to use the average instead of the expectation. So therefore, you should be able to see that, okay, so given, sorry, one more thing I want to say is that given that we have IID, YI, Y1 to YN are IID, so we expect that they share the same expectation. So therefore, the second term can be just written as max J n times the expectation of one of them. Okay, so let's just use Y to denote one of them, theta J. Okay, so therefore, this target is going to become this term. Is going to be estimated by the average. So we are going to have n, let me put it here, n times 1 over n summation I from 1 to n log p yi. And the theta J is going to be used or replaced by the MLE. That's it. So you see here, we use the same data y1 to yn for twice. One is for estimating the parameter to obtain the MLE. Second is to evaluate this average as an estimation of the expectation. Okay, so clearly this data being used for twice will introduce some bias there. And that is the thing we want to correct for. Okay, so from now on, I'm going to give you a shorthand notation for our convenience. So for this part, 1 over n times the summation with MLE, I'm going to denote this as kj bar. Okay, it's a quantity. And for this term, expectation of the log density here, I'm going to denote it as kj. So kj is our true target to be maximized. Kj bar is the achievable target we want to maximize. So therefore, there's a gap between those two. And what AIC proposes is to correct kj bar to be a better approximation of kj. So that's the goal of AIC. So why do we believe KJ bar is biased? This can be seen from the fact of what we call overfitting. So when you have the parameters fit to the same data, and then you evaluate the log likelihood based on the same data, you are going to have a very large likelihood, log likelihood, because that's how you obtain the parameter. There's no surprise of that. So essentially, we know that KJ bar is bigger than it should be. So we're going to do the correction. Okay, so what we're going to do is to prove this. This is what AIC result is. It is that the KJ bar is actually bigger than KJ by approximately dj over n. So dj is the number of parameters of model J. And we see that the larger the dj, the more parameters model J has, the larger the bias. And the larger the sample size, the smaller the bias. And so you can see from this definition that AIC is a criterion for small sample size, because if your n is big enough, you don't actually, this correction is not effective anymore. And we're going to see a corrected version of AICc later. Okay, so let's see, how do we prove this, right? How do we show this claim is reasonable? So let's just take a look at, we will just prove it. It's a pretty, I would say it's a pretty non-rigorous proof, but it's just the way AIC was derived. It uses a lot of, I would say, approximations in a very brave way. So for the sake of notation simplicity, we will drop J, which means that we only consider one model, okay? One model. So we first define the true parameter of our interest given model J. Let's say we just look at this definition of KJ. We consider theta 0 to be the maximizer of this term. Okay, so we just consider that theta 0 defined as the arc max of this expectation under F of log Py theta. Okay, it's the theta value that makes the model density closest to the true density in terms of KL divergence. This is how we define theta 0. And theta hat is still the Mle. So as the definition of Mle, arc max, it's defined as the summation I from 1 to n log Pyi given theta. So it's defined based on the data y1 to yn, while the theta 0 is defined based on a true expectation. So we see that this is the population parameter for theta such that the model is closest to the true model, while theta hat is the maximizer that maximizes the likelihood based on our data. Okay, so what we're going to do next is that we're going to evaluate the difference between those two. Hopefully that will give us the difference between KJ bar and KJ. So now here we don't have J anymore, so we say K bar and K. So to do that, we need a few notations as well. So first of all, we will define the score function. So the score function, we just write as Sy. I'll just use theta here. It's the score function based on this density, the model density. So we define that as d theta log Py theta. So it's about the one observation score function, okay? So this is the one observation score function. And don't forget that here the dimension for the score function is d-dimensional, which is the number of model parameters, and we dropped j. So there's no dj, but just d. And we also define the Hessian of the log density. Again, it's for one observation for simplicity. So we would just say that, write this as the d, probably just because this is the vector. So we'll write this d theta, probably just transpose log p y theta. And this is a d by d matrix. So we call this the one observation Hessian matrix. Of the log density. Okay, so with these definitions, let's first take a look at our K. So our K is, just give me a second. Oh, sorry, I think I defined it in the wrong way. I need to make a self-correction here. Yeah, this is a wrong definition. My bad. I'll cross this part out. But what is Kj? I'll write it here. Kj is defined as not this one, okay? So it's defined as the expectation of log density, but the parameter is the MLE. I made a mistake here. So what I want to say is that here you are evaluating the MLE using the same data for twice. And here we are evaluating the MLE under the true density F. Okay, so we want to reduce this difference because essentially the idea is that even though we don't know the true parameter theta j, but our best guess of the true parameter is the MLE given from our data. But our issue here is that we use our data for twice. After we get MLE, we also evaluate this average. And we know that will introduce some inflation bias. So what we really want to achieve is to get expectation with the MLE, but expectation must be under the true density. So we want to reduce this gap from this use of data twice to this use of data only for once. That's what we want to achieve. So with this, now we have this Kj defined in this way. And after we drop the sub-index j, we are going to write our K as, okay, so K is defined as expectation F log Py given theta hat. Okay. And then what we are going to do next is to do Taylor expansion to expand our theta hat around the theta zero. Theta zero is the parameter that makes the model closest to the true density. So we're going to use the theta zero as a way to connect those two things. The Kj and the K both involve the MLE, but here in the Kj we don't have F, in K we have F. So we're going to convert or conflate those two things by using the relationship, using the theta zero as the middle part. So therefore, let's do Taylor expansion, approximately. And here, this Taylor expansion is going to be applied to the log density. So Taylor expansion on log Py this, okay? And we are going to do the expansion around theta zero. So we write log Py theta zero. And then the first order term, that will be theta hat minus theta zero transpose, here we in the vector sense, times the score function at theta zero. That's the first order term. And the second order term is 1/2 theta hat minus theta zero transpose the Hessian theta zero times theta hat minus theta zero. Okay, we're just doing the second order type Taylor expansion on that. That's what we get for K. Okay, now don't forget that we have the expectation. So the first term is we define this term. So the one I gave you a wrong notation, this term is what we have here. It's the true model. We are going to have, not a true model, the best model parameter. So for this one, we are going to define it as K0 from now on, just for notation convenience. Okay, and the second term, we had the expectation of this. So what we're doing here is that we approximate this by the expectation we move this part out, which is not correct because theta hat is random, but we're just doing this approximation by moving the expectation only about the scoring function, the score function. And you know, based on what we said before about the score function, so if we believe that this log, or we'll say y probability of y, if we believe that this thing, theta 0, is very close to the true density f. If we believe this, then we would have this expectation of the score function equal to 0. So that's where the approximation gets in. We want to get rid of the second term in doing this approximation. And for the third term, let's see what it is. Okay, so that's just expectation on the Hessian. So we're going to use that again. So we basically say, okay, we move the expectation here. We have the plus 1/2 theta hat minus theta 0 transpose times the expectation of the Hessian. And don't forget that the expectation is with respect to y. And lastly, this. So now we are going to introduce another notation, which is the expectation of the Hessian. If you recall, if this py theta 0 is the true density equal to f, then this expectation of the Hessian is just the negative Fisher information. That's the thing we introduced before. But here we're not going to use that term. We're just going to say, let's give it a notation. So denote, let me write it here. So if we denote we just give this matrix a name, J as the negative of the expectation of Hessian. Okay, so if we define this J, then after this notation definition, we're going to say this K is approximated by K0 minus, this minus gets here, 1/2. Okay, and for this theta hat minus theta 0 thing, we also give it a notation from here. So we call that Z. We denote Z as the root n of theta hat minus theta 0. So if you have ever seen some central limit theorem type of result, we have this root n used frequently. It is a way to standardize the variance so that in the asymptotic variance n disappears. So with this definition, you see, basically we can replace this part by Z divided by root n, this part Z divided by root n. So ultimately, we are going to write this term as 1/2 divided by n, okay, n comes from here, times Zn transpose times J times Zn. Okay. This is what we obtain for approximating the K. K is the thing which uses the MLE but doesn't use the data for evaluating the expectation. Okay, so next thing is to evaluate the K bar. K bar, by definition, is the average 1/n, I from 1 to n, log P y I theta hat. Okay. So again, we are going to do Taylor expansion of the log density, just as we did here. So the same idea. So I'm just going to write it down. 1 over n summation. In the summation, we're going to have log p yi theta 0 plus theta hat minus theta 0 transpose s y I, okay, theta 0 plus 1/2 theta hat minus theta 0 transpose the Hessian y I theta 0 times theta hat minus theta 0. That's it. Okay, and now we are going to do some approximation again. So first of all, 1/2 times the summation of the first term, log p yi given theta 0. So I'm just going to write them down one by one. So the first thing, 1 over n summation log p yi theta 0. So for this one, we know it is an approximation of the k0. We have the average here, we have the expectation here, but because the theta 0 is taken as a constant that doesn't depend on our data, so if the n is not too small, by the law of large numbers, we know this is a good approximation of that. Okay, py theta 0. This is our k0. So we approximate the first term by k0. Now the second term. The second term, 1 over n, okay? This term, theta hat minus theta 0 can get out of the summation because it doesn't involve I. Theta hat minus theta 0 transpose times the summation SYI theta 0. Okay, for this term, we know we can just rewrite it using our notation z to replace the first term and also the score function. So let me just give you another notation for simplicity. So I'm going to say that denote Sn. Okay, from now I'm going to use the term Sn as the 1 over n average SYI theta 0. So we're going to denote this as Sm. So therefore, this will be equal to 1 over root n times z times Sm. Okay, I didn't do any change here. I just rewrite it using our notation to simplify this part. And for the third term, 1 over n times summation times this part. So again, I'm going to move this two terms not involving I out of the summation. So I'm left with what I would say 1 over n theta hat minus theta 0 transpose times the summation I from 1 to n Hessian yi theta 0 times theta hat minus theta 0. Okay, that's the third term. And now I can also do what? So I'm going to use another thing, that is the approximation of this average. I can move the 1 over n inside here, and the average of the Hessian can be approximated by the expectation of Hessian, which is a j here, but j has a negative sign. I want to keep that. I'm going to rewrite this term by z and this term by z. Zn, sorry, I forgot this important subindex because there's an n involved. So whenever there's a sample size involved, we should mark that. So yeah, Zn and Zn, okay. So here I'm going to have negative 1 over n, and this 1 over n comes from the Zn times Zn transpose, I should say approximately j is from here, times Zn. Okay, so for the third part, I also use the approximation, so I can link the average with the expectation. So the whole purpose of doing this is that we want to see what's the linkage between K and K bar. So how can we make them more similar? Okay, so now you see I have the, okay, there I left with 1/2 here. I should keep it in the third term. Okay, so then you see K has K0 minus this term. K bar has K0 this term and this term. So now we make K and K bar really similar to each other, and K bar just have this additional term. So after all these approximation, K bar minus K is approximately just 1 over root n times Zn times Sn. So we just want to simplify the difference as much as possible. Okay, so now it comes to our biggest approximation in the whole AIC. That is, how do we simplify Zn times Sn? All right. So what we have here is something very interesting. So look at the definition of Sn. It's the average of the IID terms. And we know that by central limit theorem, we would have root n times Sn. And we know Sn has expectation equal to 0. So it's Sn minus 0. This converge in distribution to a multivariate normal density, which is d-dimensional with mean 0. And the covariance matrix is just this, the covariance matrix of Sy theta 0. Okay, that's what we can obtain by central limit theorem. And from now on, by notation, we just define this thing, denote that by J. So therefore, we can write this density, this distribution as 0J, and J is d by d. That's the first thing we know from central limit theorem. Another interesting thing we know about Zn, we can apply the large sample theory of Mle. By the large sample theory of Mle, we are going to have Zn itself convert in distribution to normal, and it's also d-dimensional, 0 mean, and the covariance matrix for the Mle is going to take this form. One is the, so it's actually, if you think of it, it's just like the delta method if you have ever learned it. So this one will give us this form, J inverse times V times J inverse. Oops, my bad. This is V, sorry. So therefore, I should say this is the V, not J. We have used J already. J is defined as this. So you see what's J and what's V? J is the negative expectation of Hessian, while V is the variance of the score function. So what happens is that if we have the probability density function of Y under theta 0 exactly equal to the true density Fy, then we know that we derive this, J is equal to V. So therefore, in that case, we can cancel J inverse with V, and we're left with J inverse. And that's good for us. But here, we're not making that assumption as is, so that therefore, we just keep the general form. So whenever this is just not the true density, we would have this. Okay, so this is the general result for the asymptotic distribution of Mle. But what this tells us is that if we multiply J, let's multiply J with Zn. J is a d by d matrix also. So then we would have J times Zn converge in distribution to normal 0 with covariance matrix V. So then you can see the result is that the J times Zn has the same asymptotic distribution as root n times Sn. We're going to use that. So then we just make a very brave approximation by saying that root n Sn is approximately distributed the same as J Zn. Okay, so coming back to this result we want to work on, you see what we have here is there's Sn involved, but what's Sn? Sn is defined as the average score function. And now we are going to replace Sn by J times Zn. But I want to say that this is really a very brave assumption, because basically by doing this replacement, we totally ignore the dependence between Zn and Sn. We just replace it by something that follows the similar marginal distribution, but we ignore the dependence. So I would say this is a very brave approximation. Okay, and that will give us k bar minus k can be approximated by what? This thing, 1 over root n times Zn times 1 over root n times J times Zn. Zn transpose. I think I forgot about Zn transpose here. Yeah, I forgot about this. The transpose should be here. Okay, so that's why, you see, we have a more symmetric form. That's 1 over n Zn transpose J Zn. And what else? So the last thing we're going to do is just to calculate this term. And again, we approximate it by the expectation. Okay, so furthermore, we approximate this term by 1 over m, the expectation under f, of course, Zn transpose J times Zn. And J is the variance of the score function, okay? And Zn, as I recall, is the root n times the NLE minus the theta n parameter. So what can we say about this? So a very important result is to go to this. So what we have here is that we know J is considered as a constant matrix that's not random, and the randomness is only in the Zn. So one thing we can show is that this is actually a very important fact about the calculation of expectation of this quadratic matrix product. So the fact here we're going to use is this is equal to 1 over m, the trace of the middle constant matrix J times the covariance matrix of Zn. This is just a fact about this type of expectation evaluation. And here the expectation of Zn is 0, so we don't have the second term. We just left with this first term. So you can check our notes to see that exact fact for this result. But what happens here is that for the Zn, we already know its covariance matrix is this, J inverse V J inverse. So that simplifies things for us. So we have J times J inverse times V times J inverse. So we get a cancellation here, and we are left with the trace of V times J inverse. And what is that? So now finally, we need to make the final approximation. We said that if we believe the model density is the true density, we have J equal to V. So if that happens, this can be approximated by the identity matrix because of the cancellation, and that's d-dimensional. Okay, so finally, we approximate this by d over n. So you see, after so many steps of approximation, we finally approximated the difference between k bar and k by k over n. That's the term we got. And finally, this is how we get the AIC. So with this, you see that if we do the kj, okay, so we just restore the subindex j for model j. What we said is that kj can be approximated by kj bar minus dj over n. And then what is the kj bar? By our definition, is the average, is the 1 over n times the log likelihood evaluated at the MLE theta hat j. That's kj bar minus dj over n. Okay, and that's the thing we want to maximize. This is to be let me see, to be maximized, correct? Right, because if you recall in the very beginning, what we have is here, we want to maximize this term, right? And we just go to the approximation here, that's the kj bar. But we know that kj bar used theta for twice, so we want to target kj instead of kj bar. But we want to maximize it to reduce the KL divergence. That's our original goal. This is going to be maximized, but if we do multiply by negative 2n, you see, so multiply by negative 2n. What I would have will be equal to negative 2 times the summation pyi theta j hat plus 2 dj. And this is what? This is actually equal to, this is just equal to the negative 2 times the log likelihood at theta j hat. And we stick with it. We like the form negative 2 times log likelihood because of the deviance definition. And also because of the log likelihood ratio test that also uses the negative 2 log likelihood. So that's why we stick with the convention. And so therefore, you see, because we multiply this by negative 2m, this term is going to be minimized. Okay, so if this is your definition of AIC, and if we call this the definition of AIC of model MJ, if this is your definition, you hope to minimize AIC as opposed to maximize AIC. But in some, it depends on the context. Sometimes people may use another definition of AIC without a negative sign, so then you want to maximize AIC. So just be sure that what the definition of AIC is. But I would say this is the most common one, to be minimized. All right, that's AIC, and I think I need to hurry up a little bit so I can finish the BIC as well. So one thing I want to say is that in the linear model, Gaussian linear model in the linear model with Gaussian random errors, we can actually show that, okay, that's what we talk in the first part of this class. Gaussian linear model was a normal linear model. So we can see that by this definition, the AIC of MJ, let's say that here the MJ involves, theta j involves 2 parameters. So which is our beta j, okay? And also the sigma j squared, the p-dimensional coefficient vector and the random errors variance. So AIC can be shown as equal to some constant plus n times log of sigma j hat squared. So that's the estimated variance plus 2 dj. So the dimension of theta just dj. So dj here would be equal to the number of coefficients plus 1. Okay, so the reason I want to bring this up is that this AIC has a very interesting connection with the model selection criterion in the Gaussian linear model called Mallow CP. So we can actually show that. So the Mallow CP Mallow's CP. It's criteria specific to the Gaussian linear model, and it is defined as 1 over sigma j square RSSJ minus n plus 2 times dj. Okay, and this is actually approximately AIC MJ. Okay, up to constants. So we have to ignore some constants, but we keep the key terms, and they are approximately the same. So what we want to say is that this sigma j square, or I would say here, it's not, this is something we don't know, right? But in the Mallow CP, we actually use the sigma square estimated from a full model, the largest model you want to consider, to replace the sigma j square. And RSS is definitely from fitting the model J. So the logic here is that if we consider the AIC MJ, we have this log term. Okay, that comes from the log likelihood. So what we do is that probably it's better I drop the J. Okay, I dropped the J. I just call the sigma square the true sigma square. That would be better. So then you see that just starting from AIC MJ, I ignore the constant. Okay, so I can what I can do is that I could just add a constant based on this. So I could write as n times log of sigma j hat square over sigma square, because sigma square is considered as known as the true variance plus 2dj. Okay, then I'm going to do a very interesting approximation based on log. I can for sure assume that, okay, this term, this ratio is close to 1. That's something I want to say, because if the model is good, this term should be close to 1. So therefore, I can write the first term as log 1 plus sigma j hat square minus sigma square over sigma square plus 2 times dj. Now I'm going to use an interesting result in calculus. That is, if it's log 1 plus a small constant, it can be approximated just by that constant. So this is approximated by n times this. Sigma j hat square minus sigma square over sigma square plus 2dj. And then finally, you see, I get n times sigma j hat square over sigma square, okay, minus n plus 2dj. And I'm done, because I know this numerator is exactly the definition of RSSJ. Okay, so that's how we can connect the Mallow CP with the AIC. That's why people often say they are equivalent. But the key thing here is in Mallow CP, you have this constant sigma square to be estimated. That's the true sigma square. And we have to use usually people just use the full model, the largest model you want to consider to estimate that. While in the original definition of AIJ of this form, you just need the sigma j square estimate, the hat, from your given model J. You don't need to have this additional term to be introduced. But once you compare the models, you will get most same result from using Mallow CP and AIC. Yeah, because of this approximation by log. Okay, that was a very quick introduction of AIC, because previously we used 2 lectures to cover this model selection, one for AIC, one for BIC. So now I'm going to quickly move on to BIC. So just as a reminder, AIC is concerning about this term only. It's only concerning about this term. Okay, so the expectation of the log density. And there's no prior involved, because we are under the frequentist framework. We care about density or the likelihood. We don't care about the prior or posterior. But now let's move on to BIC. We get the prior and posterior involved. So in BIC, what we are interested in evaluating is the posterior of model J. So we write it's the probability. It should be discrete, right? That we have K models. The posterior probability of model J given my data. That's what we are interested in. And BIC, by Bayes' theorem, we know this is proportional to the density of my data given model J times, I should write the lowercase, times the prior of model J. And here we assume a flat prior, which means that all models are likely. So probability of M1 is equal up to probability of MK. So when they're all equal, then comparison of the posterior is reduced to comparison of the density. So our goal is just to find the J that maximize this density, MJ. But what's different here is that previously we write theta J as the parameter of model J. And we, under the frequentist framework, we assume that model J, MJ, has one true parameter, theta J. But under the Bayesian framework, we know there could be multiple values that theta J can take. So therefore, Bayesian people do not think this is equal to P y1 to yn given theta J. Instead, they think of this as an integration problem. So what it means is that we are basically taking the integral of the joint density y1 to yn given theta j. And we also need something that is the distribution of theta j under model j, d theta j. This is what we do as a Bayesian person. Okay, so we need to do integration over the possible values of theta j. While as a frequentist person, we only consider the true value of theta j. So this is the target of BIC. But once we have that, we can see something very interestingly. That is, we are going to approximate this integration, okay, and use something we call the Laplace method. I'm not going to talk about that in detail here due to time limit, but it's in our notes. So what essentially does Laplace method does is that it tries to do Taylor expansion inside the integration. And what's special about that is that we try to make the function to be integrated as exponential function. And then we apply the Taylor expansion to the exponent, and then we simplify it. And the goal is that we are going to create an exponential function whose exponent is a quadratic function. And that's what we can do with the second order Taylor expansion. We can achieve that to make the exponent a quadratic function. And once we do the integration, we're going to use the formula, the normalization constant of Gaussian density, because exponential function with the exponent as a quadratic function is very similar to the Gaussian density. So we could do that and to simplify the integral as a constant. Okay, that's the basic of Laplace method. So what we're going to do next is that for this part, so this integral density y1 to yn given theta j, okay, this is the integral we want to do. So what we write is that we just write it as exponential to the log of two terms. The density y1 to yn given theta j, p theta j, okay, d theta j. And then we apply the Laplace method. Okay, to do the approximation. And the thing we get out is the same term, but evaluated at the true value. So sorry, I should say evaluate one particular value, and we can say that particular value is our MLE. Yeah, that's what I want to say. So we can say this can be get out as the log of these two things, f y1 to ym at theta j hat times p f theta j hat. Okay, that's the first term we get out. And what we have left is the normalization constant that's going to come from the Gaussian density integration. Okay, so for that part, I will have it as just 2 pi to the power dj over 2. Yeah, and here I'm going to have the negative of the Hessian. It's the Hessian matrix of the log likelihood evaluated at, let me check my notation for AIC, just trying to be a little consistent myself. So we call the Hessian y. Yeah, so we're going to do that. The Hessian of, I would say this is not the one observation, but it's about n observation. So I'm going to write it as y1 to yn like this, and theta j hat. Okay, it's the Hessian at theta j hat, negative Hessian determinant. That's the normalization constant from the Laplace method. And this is the dimension of theta j, because this is a multivariate integration. It's not a univariate, because theta j is multidimensional, dj dimensional. Okay, so for this part, this is the determinant. But now what we are going to do is that we are going to add two more things. So we assume that the prior theta j has a flat prior. In other words, here in the BIC, we'll always assume flat prior. So the same probability for all models, and within model J, the same probability for all the values of theta j. So that can actually get rid of this probability of theta j hat. We're left with exponential log density at Mle. And the second assumption we're going to make is that this negative, the Hessian, joint Hessian, theta j hat, we want to approximate this by n times the Fisher information for one observation at theta j hat. We know that this, if we take expectation of this expectation is equal to n times the Fisher information for one observation. And that's the approximation we're doing here. We're again using the expectation to approximate the observed one. Okay, so with this, and I left it with 1/2 here, sorry. Yeah, so with this, then we can put things together. So you see, once I take the log of this part, okay, so but for this part, it comes down with the log. What I would have is the left-hand side, the log of probability of y1 to ym given mj, which is the quantity I want to maximize here, can be approximated by some constant as well. I'm just going to drop the constant plus this thing, log f y1. Oh, sorry, I should say p. The notation is a little bit messed up. The joint probability of y1 to ym at the Mle. Okay, this one comes out, and this flat prior becomes going to the constant. And what's here is that you see in the denominator I have n, and I have the Fisher information to the 1/2. So that n, you know, this determinant, this matrix is dj by dj dimensional. So once I get that out, I'm going to have an n to the power of dj over 2. And I'm going to take the log of that. So this comes down to minus dj over 2 times log n, and n comes from here. Okay, and that's it. So other things are treated as constant. So like the Fisher information for that, these were all put into the constant here, which we don't compare because we think, okay, the information is already, so we can only keep the information in this log likelihood at MLE and also the sample size M. And we ignored a lot of things, including the Fisher information at theta j hat. So you see, basically by maximizing this, and is equal to, this is going to be maximized. And again, if we multiply this by -2, we are going to see, we are going to have the -2 log likelihood. This is essentially that, theta j hat. Okay, this is essentially the log likelihood at the MLE plus -2, cancel the -1/2, dj times log n. Okay, so this is going to be minimized. And this is essentially what we define as the BIC of model MJ. Yeah, this is a very brief introduction of the BIC. We ignore a lot of details here, but the key message is to see the difference between BIC and AIC in that. In AIC, we are concerning about this, the joint density given theta j. While in BIC, we are concerning the joint density given the model, not theta j, but the integration here, it's the MJ. So the integration itself will actually make some difference. So ultimately, by ignoring many constants, we are coming to this part where the dimension dj is multiplied by log n instead of by 2 in the AIC. So that's why in many introductory level introduction, people emphasize the difference between AIC and BIC by this constant between 2 and log n. We know log n is usually, right, unless your n is super small, it should be larger than 2. So therefore, we would have a stronger penalty on the dimension in BIC than in AIC. So if you use both to select a model, BIC will tend to select a smaller model with fewer parameters, while AIC tend to select a bigger model. And this is also aligned with my preview to say, okay, AIC focuses more on the prediction accuracy, while BIC focuses more on the selecting the so-called true model. So ultimately, this is a philosophical issue about which one you trust more, because several people question BIC for its practicality, which is that, okay, your philosophy or your theoretical goal is to find a true model, but we know that all models are wrong. So we cannot really believe that one of our candidate models is a true model. So that seems to be a very severe attack on the foundation of BIC. But on the other hand, people are saying, okay, given that we prefer sparsity or parsimony philosophy, then BIC selects a smaller model. That seems to be quite satisfying our goal. And those BIC people, they would attack AIC by the fact that, so this is something I will talk last, probably will go a little longer, hopefully you don't mind. That is, if we think about the perspective, okay, what I mean. So just take a look here. So we think BIC, so the comparison of BIC and AIC. So based on their philosophy, we know that BIC is trying to approximate -2 times the posterior MJ given, PMJ given Y1 to Yn, right? That's from the Bayes rule. We are interested in the posterior. This is the thing BIC want to approximate. And of course, we ignore some constants because we're on the log scale. But this will ultimately give me something. So BIC MJ. So if this will give me, if I want to write out the posterior of K models based on their BIC, I can say that the posterior is approximately to the exponential of -1/2 divided here BIC MJ with normalization. Okay, so I'm going to say J from 1 to K. J prime from 1 to K, exponential -1/2 BIC MJ prime. Okay, so I can have this relationship. In other words, with the BIC of the K models, I can approximate the posterior of each of them, while AIC is not. So remember that AIC MJ is trying to approximate -2 times expectation of the log of y1 to yn, okay, given the parameter theta j, true parameter theta j. This is the thing AIC aims to approximate, and it's only about the density part. It doesn't have anything to do with the posterior. So therefore, if we want to make it into a posterior, and also here we think under the frequentist framework, theta j represents mj. Okay, so therefore here under the frequentist framework, because you consider theta j to be the only parameter, I can directly write this as log y1 to yn mj. Because you think, okay, the distribution of the parameters theta j under mj is just concentrated on one value, one point mass, that's theta j. So we write it this way. So therefore, if we want to write this in terms of the posterior under the AIC, we are going to have this interesting fact. We must consider the prior. We're not done yet. So it should be approximately equal to the exponential of -1/2 AIC MJ, okay, times the prior MJ. The prior is not in the AIC, so we must account for that. And J prime go from 1 to capital K, exponential -1/2 AIC MJ prime times prior MJ prime. Okay, so that's the AIC. But if we just try to follow this and then just to make those two equal to each other, okay? If we set them equal to each other because they're both the posterior, then I can solve the prior assumed by AIC. And that's a very interesting thing. That will give me the prior of model NJ will be proportional to exponential 1/2 times dj, the model parameter number, times log n minus dj. So essentially, if we put AIC under the BIC framework, under the Bayesian framework, we see that AIC does not assume a flat prior on models. Does not assume a flat prior. And what it does is, what's criticized by the BIC people is that the prior, how can the prior involve sample size n? Prior should be your prior belief without seeing data. But what AIC essentially does under the Bayesian framework is that its prior on the model depend on the data sample size. And you can see that because the larger the prior, the more tendency AIC will tend to believe in that model. And its belief is better, or it believes more in the more complex model when the sample size goes larger. And it believes in the simpler model when the sample size goes smaller. And this was criticized by the BIC people as it violates the Bayesian assumption that is prior has nothing to do with data. But on the other hand, if you think from the like a practical data analysis perspective, you may think, oh, AIC's assumption seems to be reasonable because if I have a larger sample size, I can afford a more complex model. So that's why AIC tends to select a bigger model as sample size grows. Seems to be not a disadvantage if you think from the data analysis perspective. So again, I want to put it in the way that this becomes a quite philosophical thing between the debate of AIC versus BIC. And I would say previously there are many people just supporting BIC, but nowadays people are finding excuses or rationale for AIC from this perspective. And you can think of it further if you're interested, but in practice, okay, back to data analysis, I would say people can use both. Yeah, you can use AIC or BIC to justify your choice because anyway, after you saw our derivation, they are both relying on a lot of approximations in their derivation. So unlike cross-validation, which is model-free. Yeah. But so I think the take-home message is that now you can see statistics, those criteria are quite philosophical if you really want to understand what they're doing. And there's no simply the best one. Yeah, that works for everything. So finally, to address people's question that, okay, AIC tends to select a very big model, while BIC can select a much smaller model, so we prefer BIC. Related to that, people say, okay, the reason you think AIC doesn't perform well when your sample size is not big is simply because that Taylor expansion used in AIC, if you recall, we have that Taylor expansion to derive that K0 and K, right? The K related to K0 and K bar related to K0. So that's just where the Taylor expansion doesn't work well. So related to that, people propose the AICc, which is called a correction. Okay, corrected AIC. And this tends to select a smaller model and it becomes more similar to BIC. And that's quite interesting. So that's why people who advocate AIC saying that, okay, if you don't like the overly big models developed by AIC, you should consider to use AICc. And that issue is no longer evident. So AICc is recommended to use when the n over dj is less than 40. So in other words, your sample size is not too big compared to your model parameters. So it has an additional term. Let me just write it down. AICc for model MJ is -2 times the log likelihood at the MLE as always, plus 2 times dj as in AIC, with the third term, and that's 2 times 2 dj plus 1, n minus dj minus 1. So you can see that when n is much bigger than dj, this term will actually go to 0, right? So you can ignore the third term. But when that's not the case, the third term may not be too small, so you want to keep it. So essentially, the third term increases the penalty on dj. So that therefore, you will tend to select a smaller model, just as BIC does. Okay, so that's what I want to say for AIC and BIC. And you can check more details in our lecture notes. And yeah, there are many interesting discussions related to this topic. But just the take-home message is that in the case when you don't have a large enough sample size to afford cross-validation, think of AIC and BIC of your choice. Okay, so that's all I want to say for this class and also this lecture. So we will have your presentations this Thursday starting at 9:30. Please remember to send RTA Dongyuan your recordings if you cannot present in person, if that time doesn't work for you, because I know some of you are in a different time zone. But I think that doesn't apply to all of you who are present here. Otherwise, you will not attend the lecture live. And also prepare to send your slide. So we'll just do screen sharing on one computer, and we can save the time for switching screen sharing. All right, so see you on Thursday.
Can I ask a question?
Yeah, sure.
Do we multiply by -2 just to make it more like deviance or comparison with deviance?
Yes.
Okay, and I was also wondering, and AIC and BIC, is it just for comparing nested models?
If you think from that derivation, I don't think so. Yeah, so there's no requirement on nested model. That's different from the likelihood ratio test. likelihood ratio test requires that to derive that, the asymptotic chi-square distribution.
But they all need to have the same distribution. We're assuming the same distribution between different models.
You mean for AIC or BIC or for the likelihood ratio test?
For AIC and BIC.
No, they don't. They don't, because AIC and BIC, it's actually a measure that's just depending on your data. So themselves are random. Yeah. So therefore, we don't need to. We are not talking about the AIC, BIC themselves, the distributions of them. So that's why there's no such consideration about the assumption of nested model.
Okay, great. Thank you.
No problem. Bye.